All right. Okay. So we are into a heavy-duty topic, but an important one. So we are into chapter 8 of the deep learning book. Oh, actually, I did mention another current topic. I was mentioning last week, I think, there was an important conference going on in New York this last week, the AAAI 20 conference. And the main panel session was the 3 Turing Award winners speaking about what is to come in the future. They received the award for deep learning. And so they were all discussing what is to come in the future. And it was interesting. I just saw a newspaper account of it, Wall Street Journal account of it, summary of the main thing that they were discussing is the area of machine learning, which is beginning to be called as self-supervised learning. So we have talked about supervised learning, we have talked about unsupervised learning, and we have talked about semi-supervised learning, right? Supervised learning with labels, unsupervised learning, no labels, just a data set, learn a probability distribution or learn the clusters and that kind of thing. And then semi-supervised is some of it is labeled, some of it is not labeled. Self-supervised is the ability to use whatever data is there and from there obtain the possible labels that could be had and learn from that. Sounds like a strange problem. How could you do self-supervised? But there's a very simple example I came across of what is self-supervision. They had this simple picture of a cat, a cute cat, right? A body of a cat. The cat has a very cute face, and it has got two pointy big ears on the top. So they illustrate the idea of self-supervision by saying, well, let's say you recognize the face of the cat. It's got the eyes and the nose and the mouth and so on. There's a cat face here. And you can now use that context saying, okay, it's a rectangle around just the face, not the ears, just the face. And now you have that information to predict. If you know the face of the cat, which you have recognized maybe using supervised method, and now you can predict, well, where is the ear of the cat now? It's going to be on the top right and the top left will be the 2 ears of the cat. So you're predicting the label for the ears and saying, okay, so let us use that as supervised learning data. So you're now able to improve your performance on recognizing the cat's ears, right? So there is an instance of using context to self-supervised, and it's neither supervised nor semi-supervised or unsupervised, but it is self-supervised. An up and coming topic, which you may want to think about if you want to be on the latest and where is the frontier. Self-supervised learning, according to at least the 3 Turing Award winners' opinion about what's to come, which kind of reminded me that we are in chapter 8 of the book. Benji is one of the authors. He was one of the Turing Award winners. So we are kind of going along our version of that same material. So we have finished, we did all the preliminaries earlier on in the semester. And then we went on to talk about deep feed forward nets. And then after that, the next topic was regularization, right, which is generalization ideas. And this is chapter 8 of the book, is the optimization techniques. So let's take a look at here. And this is a wide range of things. And just a look at the table of contents itself is quite illuminative. So we begin with the role of optimization versus generalization. Then how does learning differ from optimization? And then what are the challenges in optimization here? We bring in the idea of risk, empirical risk, surrogate loss, Surrogate loss is rather than use the actual way to evaluate the performance, we use a surrogate in place of it. And then, of course, methods we're already familiar with, batch and mini batch and data shuffling, ideas like that all play a role here. And then the most famous choices for the optimization algorithms are stochastic gradient descent and momentum-based algorithms, a particular variation called Nesterov momentum algorithm. So this is a nice menu of choices you have to pick to be able to implement any machine learning. And then, of course, strategies for initializing the parameters, rather than simply go with arbitrary ones. Is there any strategy for that? And then methods with adaptive learning rates, AdaGrad, RMS prop, Adam optimizer, which seems to be popular method, which is an adaptive method. And there are all kinds of questions come up throughout. So many of these algorithms, which is better? What are the advantages, disadvantages? So many things one could ask about these questions, all different algorithms. And then there is even, let alone first order methods, second order methods, which go into computing not just the gradient of the loss function, but also going about computing the Hessian of the loss function, which is not the first order derivatives, but the second order derivatives play a role. And then strategies for choice of some of these things. So there's a lot here. So we'll see what we can cover in 2 lectures, because there is still more stuff to be done. So we have reserved ourselves 2 lectures to cover this topic. Right. Okay, this slide simply says optimization comes in if you're doing a study of machine learning, deep learning. Optimization comes in several contexts, right? Even very simply, if you're doing PCA, PCA is not a statistical method as such. It is simply a linear algebra technique where we are trying to reduce the dimensionality of the space. So even there, you need some kind of optimization. In PCA, we look for an encoding. We map the inputs X to another code C, and then from the code, you can get back the original X by having an inverse function, which typically takes the form of multiplying C by some D, matrix D. And so the task becomes what is the optimal code? So every X, given a vector X, we're producing a vector C, is the code. And so what is the optimal way of doing it? So you need some kind of a measure. You need the difference between X and the reconstructed G of C should be possible according to the L2 norm. And once you obtain that value, you can reconstruct using that value C star. From that, you can reconstruct. So there is some type of optimization going on. What is the optimal value? There are also optimizations with respect to proofs and design, such as the squared error objective, same as maximum likelihood, that kind of a thing. Of course, those are all smaller topics, but the big topic in deep learning and optimization is neural network training. It is the most difficult optimization of all, and so we talk about a criterion function such as if W is the set of all weights in the network, JFW is how good are these weights, and this is computing some expected value with respect to the data of a probability distribution of the model. Is a supervised problem, y given x, and here is the regularization term, typically something like that, is something you want to minimize. So you have to keep in mind there are a couple of mathematical equations that are central to any deep learning system you are implementing. One of which is the equation that corresponds to the model you are using. The other one is the equation corresponding to the loss function. Right? So typically, like for example, the model is coming to play a role here. And this is the expression for the loss function here. So both of them are important, and we'll take a look at the regression problem to see what these are. Okay. All right. So our goal is to find parameters W of a neural network that significantly reduces the cost function. And it typically includes a performance measure evaluated on an entire training set, as well as an additional regularization term. So we have, for example, if you the regression problem, the squared error with respect to every output the model is producing and what it should be producing, the difference between the two is squared and add it over all the data set you have. And that is a measure of the performance. We add a regularization term to it. So we want to reduce that cost function. Yeah, here is the one that I mentioned specifically. So you can think of it as a deep learning is an instance of a recipe. So you need 4 ingredients for a deep learning task. First of all, of course, you need a data set. Like I mentioned, the performance of all the students in the class would be a data set. And you need a cost function in the sense, what is it you're going to try to optimize here? And then you need a model that is going to be built into the cost function. The model is going to generate the output. And then you have to have an optimization procedure to set the parameters so that the cost is minimized. What I did here was to specifically, that seems a very abstract to say it like that. Specification dataset, cost function, model optimization. Let's say you're simply working with a regression problem where for an input you need to predict an output value, a continuous value, rather than a class label. For a linear regression, you have a data set X and Y, it's shown as a matrix in the sense. For every input vector, there's a scalar value output Y. And then, of course, you have many vectors, so we can show that as a matrix X. That would be your data set. And the cost function we just saw in the previous slide has this form of the cost function is the expected value of the log model here. And what is going on here is, let's look at the model. What is this model? This is saying y given x is a normal distribution this is a linear regression problem where we have x transpose y, x transpose w plus b, and we have a normal distribution with output y has this mean and this particular variance variance. Yeah. So this is we're saying that the noisy output, there is an underlying linear model, and then there is a noise model on top of it. So we're saying the model of linear regression is a normal distribution here, the output y given the input x. So we're predicting the output like that. It can be noisy added to an underlying linear function here. So the cost function takes that into account. That is the model. It is saying the expected value, which means it's of the log actually here. So what is happening here is we take the likelihood function. If you have a probability distribution over a set of samples, you can multiply it for every sample. You get the likelihood function, and you take the logarithm of the likelihood function. All right. So that is what is happening here. This is the log likelihood function here, and of course we want the criterion. If it is likelihood you're working with, you want to maximize that likelihood. We want to write it as a minimizing thing. So we have a negative sign over here. So we are minimizing the log likelihood, and then we are adding on this regularization term. So this is what is being specified for the regression problem, that we have a model and then we have a cost function. Of course, in a lot of binary classification problems or the multi-class problem, you have the cross entropy loss function. In this regression case, we don't have cross entropy, but we are using the likelihood function playing a role, and that is shown to be equivalent to the sum of squares again. So this is the model, it's the cost, and an optimization algorithm for solving where the cost is minimized. If this is the cost, we want the W's to be such that the cost is minimized. How do you do that is to take the derivative of this quantity and do gradient descent, start with an arbitrary value of W and keep moving in the direction where the cost is going to be reaching a minimum, local minimum, right? Anyway, this is what happens in any deep learning task is you have a data set, you have a cost function, you have a model specification, you have an optimization algorithm solving for where the cost is minimal. Assuming you are actually figuring out the parameters for the task. But there are like in this project 3 you're going to be doing, it's already done for you. You've got already the values available. The optimization has been done in a multi-task. So you can use whatever values somebody else did it. Okay, anyway, in those kinds of tasks, in like natural language processing, like the kind we saw Obama was doing, I suppose that involves some natural language processing. Common to invest days and months of time, hundreds of machines to solve a single instance of a neural network training problem. Right. There's one more thing that was being mentioned in this AAAI 20 discussion, just I think yesterday or day before it was. Other than talking about self-supervised learning, one more thing that came out was, of course, they're aware of the kinds of hardware that are being developed today, that they're orders of magnitude faster GPUs and so on for solving these deep learning type of problems. So there is a big effort going on to produce super fast machines for doing this. So when I say it takes hundreds of machines to solve a single instance, that might be, it is so 2018, right? In 2018, you said that, right? It's old stuff. 2020 might be a different picture. It doesn't require that much time to solve it. But so as you can see, that's a varying thing. Anyway, the problem is so important and expensive. Specialized optimizations algorithms. So why are there so many optimization algorithms? Is because of its importance and its criticality in applications. So this is a big topic again. How could we discuss this topic? Is we begin with how optimization differs. Training optimization differs from pure optimization. Why is the challenge of optimization difficult? And we look at optimization algorithms, initializing parameters, so on. I think we saw it in the table of contents. Combine simple optimization algorithms to higher level procedures. You're already familiar with deep learning frameworks. They all include some methods of optimization. And these frameworks are building blocks for designing, training, validating deep networks through a high-level programming interface. And they're optimized for performance, for parallelization, for GPUs. That's what you're doing on Google Colab and so on. I saw a pretty picture on this one. These are all the different companies like Microsoft, Facebook, Google, Amazon, and all their frameworks, such as PyTorch is over here with Facebook's, and then there is with Microsoft Gluon, and that's between Amazon and Microsoft, and with Google you have this TensorFlow and Keras, and some of the other things are Torch and Theano are kind of outside of it. They were the original startups. An example is Keras, a library in Python running on top of TensorFlow and contains implementation of building blocks such as layers, objectives, activation functions, optimizers, tools for working with image and data and text easier. So this is the topic we are looking at is what is inside these boxes, inside these library functions that are the optimizers. And of course, this was just a small example where you're compiling a model and then you're specifying the optimizer is SGD, loss is categorical cross entropy, so on. I mean, that's all it takes for you to invoke these things when you're writing code. But anyway, we're looking under the hood. And I found all kinds of nice movies and all that kind of thing here. Don't know if it works. No, it works. Okay, this is the movie that. So here we have a particular loss function here. These are all contours of constant density of the loss function. And there is the minimum here and how we are proceeding along here. Different algorithms, simple gradient descent here. And this is coordinate descent. And alternately, we are proceeding on different features. And then it shows what happens in stochastic gradient descent with the noisiness involved in approaching the minimum because you're using small mini batches. All right, let's see what we can say about how learning differs from optimization. We've already talked about it. So maybe there's something more here. All right, the topics here are learning versus pure optimization, empirical risk minimization, surrogate loss functions, and early stopping, batch and mini batch. Okay. So what are the main ways? Machine learning acts indirectly as opposed to general optimization. We care about some performance measure P defined with respect to the training set, which may be intractable. We reduce a different cost function in the hope that doing so will reduce P. It's a very simple idea. Supposing you're trying to just simply build a classifier between cats and dogs and so on. We can say, well, how should your algorithm be? Make as few mistakes as possible. A cat, when an image is labeled as a cat, it should be a cat. When it's labeled as a dog, it should be labeled as a dog. So, what is your criterion? Is make that mistakes as few as possible. We can say that is our measure of performance. P is the accuracy of the classifier. But we don't typically use the accuracy of the classifier uh, as the objective function that is to be minimized or maximized. Accuracy should be maximized, error should be minimized. So we use a different cost function, which is in terms of the parameters, in the hope that doing so will reduce P. So we're using the cost function to reduce P. And so in pure optimization, minimizing J is a goal in itself. Whereas in machine learning, we do this indirectly through some surrogate function. And of course, these optimizing algorithms may be related to a specific structure. Okay, again, the issue there is why can't we do that directly? Is because it might be an intractable function. Okay, simplest example is the idea of the simplest early version of deep learning was perceptrons, and it was originally defined in terms of getting it right or wrong, and there was no way to take derivatives of that. How do you change the weights? Is you need to take derivatives of your loss function, and if it is a discrete function like that, you cannot take derivatives. So gradient descent is not possible. Stochastic gradient descent is not possible. And so there is one good reason why the objective function such as accuracy is not the appropriate term to learn in using gradient descent, right? Okay. So anyway, a typical cost function can be written as an average over a training set. Keep in mind, this is when you say expected value, where did that come in from? Expected value is typically a sum of some things divided by the total number. It's expected value is simply the same as mean. And that's what we're doing here. It's an expected value. L is the per example loss function. Per example. So that could be like the value that's being output and value it should have been. So what is the difference between the two? Square of that. That's a per one example loss function. And when we do expected value E, we're saying do that over your entire data set. course, we add that, and of course, dividing it by the total is necessary to compute expected value. So that's where the E comes into play. And f of x theta is the predicted output when the input is x. And p hat of data is the empirical distribution that is based on your data set that you have. So we can state it very generally like this. The cost function for any deep learning algorithm can be written like this, right? And you have to, of course, make some choices uh, as to uh, as to what these forms are. Is it sum of squared errors or cross entropy and so on? And supervised learning, y is the target output. So this is the typical cost function. So we consider the unregularized supervised case in this discussion here, and trivial to extend to cases where parameters theta and input are arguments. Right. Anyway, the future of machine learning, according to the discussion I just mentioned, is you want to now talk about supervised learning, unsupervised learning, self-supervised learning. I'm not sure whether that's going to lead to a complete branch of machine learning, right? There's supervised learning, unsupervised learning, semi-supervised learning, or is it going to be just a subset of unsupervised learning? Because you are not given the labels, and you have to learn the labels so that you can use supervised learning, right? So it could be a subfield of either supervised learning or unsupervised learning. So it's self-supervised. I was just searching to see what's the papers on this topic. There isn't that much on it yet. There is, but there are a few papers which is going back to 2018 or so, right? So take a look at it on self-supervised learning. All right. So objective with respect to data generation is risk. We would prefer to minimize the corresponding objective function where the expectation is across the data generating the distribution P data rather than the finite training set. Well, this is saying we really should be obtaining this over the true data distribution rather than the empirical data distribution. We got some small set of data here or some subset of data, but really the goal of machine learning is not minimizing that, but it is minimizing this. What has happened is the hat is gone here, and then J now gets a star over here. That's the ideal loss function we're trying to minimize, right? And this quantity is known as risk. Well, there's so many words for this thing, objective function, so on. So that is the risk. I guess the value of that is the risk, the minimal value. So the true risk is the one given on top, and the empirical risk with M training examples. We have now gotten rid of the expectation here, and we have put a summation I equal to 1 through M, 1 over M of this quantity. So it's just defining what do you mean by expected value here. It is just a sum over all these values. So this is simply like the sum of squared errors. This is the model output based on the parameters. This is the ideal output. And this is how we are defining the squares and summing over all the samples. So it's just stated more generally. So empirical risk is minimizing the average training error, still similar to straightforward optimization. But empirical risk minimization is not very useful, prone to overfitting, can simply memorize the training set. All right, so this is making a fine difference here. Because otherwise it all feels like just ad hoc, pick this and that and so on. What's being done here is to try to express it in a systematic way, that this is a set of principles that are being actually used here. So it says, if you simply work with p-hatted data, it's prone to overfitting, can simply memorize the training set. Stochastic gradient descent is commonly used, but many useful loss functions have 0, 1 loss. That is simply, you're saying if it is a mistake, it has a loss of 1. If it is correct, it's got a loss of 0, but it has no useful derivatives. Derivative is either 0 or 1 and undefined everywhere. So we must use a slightly different approach. And quantity we must optimize is even more different than what we truly want to optimize. So that is where we end up with a different thing than what we are going to be measuring the performance. And I don't know if I mentioned, there are like dozens of different performance measures depending on the particular task you are working with. Accuracy is just one of them, one of the things. Is another problem where you measure the performance using dice coefficient. So this is where the word surrogate comes in. Surrogate loss is a law. So if you're wondering why is all this probability showing up in machine learning so quickly, is because we want an alternative. It's a surrogate model and naturally expressed in terms of uncertainties and probabilities. So, and then as soon as you express things probabilistically, we can talk about log likelihood functions and log likelihood over a data set. And so we use surrogate loss, negative log likelihood of the correct class. See, this is negative log likelihood of the correct class is a surrogate for 0, 1 loss. So we replace that. It allows model to estimate conditional probability of classes given the input. So all of this is being expressed in a systematic way as to where this came from. So the surrogate surrogate may learn more. It's kind of interesting. Saying you're having a problem with working with derivatives with the true loss, we replace with this likelihood, and now we're saying, well, it can be even better. Tested 0, 1 loss continues to decrease for a long time after training has reached 0 when training. So this can take the classes apart even more, which is kind of another interesting property. And the learning does not stop at the minimum. And then batch algorithms is the next topic. We're using small sets. What is that? Yeah. Okay, I hope I can go on. I have a little bit of a cough. Okay, tell me. Hmm? Hmm. Is this a slide you want to look at? Previous one? This one here? Hmm? Yeah. So it says test set 0, 1 loss continues to decrease for a long time after the training set. Yeah, by using a log likelihood surrogate has reached 0 in training. So by using a probabilistic model, we can continue because it never really approaches 0 when you're using a probability. Whereas with an accuracy number, 0, okay, 0 loss, what else is there to do? I got everything right. Whereas, so this is the difference between a probabilistic model and maybe a discrete model. The answer is 0 or 1, you're saying. It's a cat or a dog, right? I mean, that's how the problem is. But then we're saying we're going to be calculating the probability of cat and probability of dog. And that is a probability which never quite gets to 1 or 0 exactly. There will be some small value associated with it based on your data set and parameters and all that. So it says rather than working with get it yes or no, the probability should be used so that the likelihood function is made as small as possible. So it never really approaches 0 or 1. So you keep on heading in that direction. That's the main point. Yeah, that's true because in all these neural networks, it always gives you some probability. It says 0.9999. It will say if it, instead of saying 1, you're actually calculating probability like that. That is the power actually of probabilistic reasoning. Um, I have encountered this in a different context. For example, in forensics, people will say, "This is the suspect who did this. I'm 100% sure about it." And that is a discrete type of thing, yes or no. Right? There is always some small possibility that this person didn't do it. Maybe a very small probability. So it allows for that. There's a bit of fuzziness in it. Fuzziness comes into play. That value, and it is so when you formulate way. That's what's going to happen. It's going to always going to be like that. It's never going to be one, unless of course you can round off your 0.999999 as one. The actual value you're going to be computing is a value like that. It depends on the precision with which you're calculating these, right? So this is saying the surrogate of working with the probabilistic model maybe has more power. And the original idea that people started doing this perceptron, they were not thinking like this. They say it's a yes or no type of model. How do I change the value to a parameter? That's why you need gradient descent to do that. So there is a simple version of gradient descent we're actually using perceptrons as well. Approximate. With perceptrons, right? It's a very simple model, which it's a two-class problem. And you're trying to figure out it's one class or the other. And it does not use gradient descent. The perceptron learning algorithm does not use gradient descent. What does it use? It is trying to use a plane. You might have seen pictures of perceptron. I got points on this side, points on the other side. It's trying to draw the best possible line or the plane between the two. That's what a perceptron tries to do. So how does it change its value? It has a simple learning algorithm, which says, well, if a sample was misclassified, it's a plane like this you've drawn, right? You're somewhere in between your learning stage. You've drawn this thing. There's one sample going on the wrong side. The perceptron learning algorithm says, simply add the value of the sample you got over there to the weight vector. You have weight vectors and sample vectors. They're all the same dimensionality. So saying there is a vector sitting over here. I add that vector to the current weight you got. Add it, simply add it. So that has the effect of moving the plane this way or that way, typically to make it right. It moves in the direction of making that one right. So that is how they define the original perceptron learning algorithm, was simply to add the misclassified sample to the weight vector. And that algorithm was mathematically shown to produce the correct answer as long as the points were linearly separable. If the points were linearly separable, this particular algorithm of adding the misclassified sample to a weight vector will find the right answer in a finite number of steps. Got a learning algorithm now that will actually find the truth. But if the samples are not linearly separable, it will keep on turning around. It will never stop. It's a procedure rather than an algorithm. Algorithm is guaranteed to converge to stop. A procedure is just a specification of computational steps which may or may not halt. It gets into theory of computation and the halting problem and all that. So that was the original perceptron algorithm, which is guaranteed to find the solution. But it did not use a surrogate loss function. And so you want a formulation, and it can be shown that adding that loss can somehow be derived from the idea of gradient here. Although there's no strict gradient, what is the loss function is accuracy. There's no derivative available for it. But we have a more general model that we want to minimize this. We're not saying get it right, absolutely all the points to be classified one way or the other. So we are relaxed cat and dog. We're simply saying, make as that's what we are moving away when we came up with a more general algorithm. It became gradient descent. We are taking the gradient of the objective function, and then there's a stochastic version of it. Right? What is also interesting is the idea of gradient descent, stochastic gradient descent have been around for a very long time. They've been around for 50 to 60 years. The idea of gradient let's say the beginning is here or on this side, then you got to increase the values to get it. If you're on the other side, you have to decrease the value. So that's where the gradient direction comes into play. So you proceed to that point. And that idea has been around. The idea of stochastic gradient descent has been around. And what is interesting is that even all the algorithms today are based on gradient descent, stochastic gradient descent. The only issues we're talking about here are this, learning and versus optimization, the generalization principles, the regularization principles, right? So that's an interesting observation about the nature of these algorithms. So in machine learning, we are doing optimization, which is a very old topic, but we have a twist to it that we want this generalization, which the optimization people did not deal with. And so that's why there's all this discussion about, is this just a problem of optimization? So training does not have the local minimum, all these issues. Anyway, there's a lot to read about and appreciate here. And I'm not going to be just able to cover all of this. I think we can have a whole course on optimization or generalization. Right? And there are all kinds of interesting mathematical issues here about working with samples, why the stochastic gradient descent works, and when you're working with samples, what happens, small number of samples, all these batch and all these ideas, stochastic online methods, mini batch size. Yeah. Yeah, what about these mini batches? Yeah, like these batch sizes small, you are and but they're not usually very large. And regularizing the effect of small batches. I'm just trying to cover the highlights here. Okay. So it's saying landscape of the loss function is not necessarily a convex goal shape function. So we are definitely dealing with non-convex goals. Actually, there are a lot of papers people have written saying, well, I have come up with a good algorithm for non-convex. The neural network people have said it doesn't matter. We don't necessarily need to have such an algorithm that's absolutely going to find the global minimum. And we can do pretty well. So there are all these issues about some of these challenges in optimization. whole bunch of numerical patterns that one can qualify and mathematical. First topic, for example, is field conditioning. So this is referring to the nature of the function, and the field conditioning is defined in terms of the Hessian nature. So we're not only looking at the gradient of the surface you're dealing with, the loss, we're also looking at the secondary. What a secondary factor in so gradient of is about this is going one more level. That is captured by the Hessian. And we are talking about you have compute the eigenvalue, eigenvectors, Hessian, and then you take what is the largest eigenvalue and what is the smallest eigenvalue, the ratio of the largest eigenvalue, smallest eigenvalue. That is very large. So there are tests for determining whether the surface you're dealing with is ill-conditioned. So this gets into somewhat complicated topics. Ill-conditioning of the Hessian condition. This is an interesting slide which goes into where does the second derivative all come into play. It's saying supposing here f of x is not the input output, it's just the loss function. And we're using here Taylor series. Any function can be written in a Taylor series, right? So this is saying f of x plus x minus x naught times g is the gradient. So you see, remember your Taylor series for an arbitrary function. We are not multi-dimensional loss functions, and we are expressing that g plus 1/2 of x minus x naught h of x naught. So we use g for gradient, h for Hessian, which is nothing but in Taylor series we use f prime, f double prime, and f triple prime, right? That's what Taylor series look like. And we're saying forget about the third order terms, third derivative terms, first and second derivative, so approximately equal to. And so that is where the Hessian comes into play in expressing the complexity of the loss function you have. Goes back to Taylor series explanation. And it is discussing here ill conditioning becomes a problem when those terms have these kinds of relationships. And to determine whether ill conditioning is detrimental, monitor. So to determine whether the surface you're dealing with is ill conditioned, you can determine the Hessians and so on, and there are checks for doing it. So learning is very slow despite its small. Anyway, we're just getting happy. All right. Is the TA here today? Okay, I think your wish might be satisfied. Is there anybody here with the quiz? If there is no quiz master, there is no quiz. Are you waiting with the quiz? Oh, great. Okay. All right. Great for me, but not for you. Maybe. Okay, so you will conduct it. All right. Thanks so much for doing it. Okay. Lokesh couldn't be here. You are? Ronak. So Ronak is, if you don't know Ronak, it's about regularization. The topic of last Monday and last Wednesday. Next week's topic will be on optimizing. Okay. Hopefully you learned something from this. Thank you.